Hello, my name is Hongda. I work as a postdoctoral researcher at the Center for Environmentally Beneficial Catalysis, which is a research facility affiliated with the University of Kansas. I'm excited to share with you some recent results on isobutane ozonation through this letter from emerging scholar review.
The U.S. is endowed with substantial amounts of natural gas liquids as collateral products of shale gas extraction. They represent a valuable source of chemical feedstock. Converting them to oxygenated products can not only provide chemical feedstock, but also makes it easier to transport them as liquids from the locations where they're produced. The challenge is to activate them at mild conditions with high carbon economy. Fixing the carbons in chemical products that can be recycled rather than flaring them as carbon dioxide also promotes sustainability. In this work, we evaluate ozone-based activation of isobutane as a model substrate. We chose isobutane as there is currently an industrial process for oxidizing isobutane to liquid products that can serve as a benchmark. We choose ozone as the oxidant as our group has previously shown that ozone can activate CH bonds at ambient pressures. The oxidation of isobutane with O2 is a well-established commercial process. It is carried out at 130 degrees centigrade and 4.1 megapascal to maintain liquid phase conditions. The reaction produces predominantly tert-butyl hydroperoxide and tert-butyl alcohol. The reaction conditions prompt the question if isobutane can be activated by ozone at even milder temperature and pressure. Actually, gas phase isobutane ozonation has previously been studied. At 50 degrees centigrade ambient pressure, about 50% isobutane was converted in only about 15 minutes. However, the tert-butyl alcohol selectivity was only 52%, with substantial formation of products from carbon-carbon bond cleavage, which is not desirable. Here we investigate if isobutane ozonation can be more selective toward tert-butyl alcohol if the reaction is performed in a liquid phase at lower temperature and higher substrate concentrations. In the biphasic system, we anticipate that the reactions will occur in both the gas and liquid phases. The primary competing reactions are isobutane ozonation and ozone decomposition, which are known faster in the liquid phase compared to the gas phase. The ozone utilization is dictated by the relative rates of these two reactions, which are tunable by isobutane and ozone concentrations. Also, the presence of protic additives promotes the hydroxylation pathway. For the experimental studies, we use a typical power reactor. Fortunately, the required temperature and pressure to maintain isobutane as liquid are quite mild. The isobutane is charged into the reactor from a syringe pump. A sample loop is in the line to add desired amounts of water along with the isobutane. An external reservoir supplies a mixed stream of ozone, oxygen, and nitrogen. We observe that tert-butyl alcohol, acetone, and carbon dioxide are the only major products. First, we varied the ozone partial pressure, which shows only marginal effects on the product distributions. Within this pressure range, the alcohol yield is maximized at 0.34 megapascal, suggesting that the relative rates of ozone decomposition and hydroxylation strongly depend on ozone partial pressure. At the optimum ozone partial pressure, we evaluated the effect of water quantities added initially to the reactor. Again, we observe only marginal changes in the product selectivities. However, water significantly enhanced the alcohol yield. Comparing with gas phase ozonation, liquid phase operations significantly improved tert-butyl alcohol selectivity. In contrast to ozonation, the oxidation with O2 produces tert-butyl hydroperoxide as well. On the basis of these results, we propose the following reaction pathways. Ozone decomposition and isobutane ozonation are the two competing pathways for ozone consumption. The first step involves the formation of the hydrotrioxide adduct from isobutane and ozone. One of the oxygen-oxygen bonds in the adduct may cleave. Either tert-butyl peroxyl radical forms and produces the hydroperoxide upon hydrogen abstraction, or the tert-butoxyl radical forms. It may as well undergo beta scission to produce acetone and methyl radical. All these reactions occur regardless of the presence of protic additives and are slower than ozone decomposition. The solvation effects of protic additives further lower the energy barrier for the hydrotrioxide decomposition by forming the ring structure. This pathway may promote the overall ozone utilization and the alcohol selectivity. Now, to summarize our work, we achieved faster liquid phase isobutane ozonation. Ozone utilization is enhanced by protic additives, as well as a tunable ozone concentration in the liquid phase. We gained insights into the reaction pathways of isobutane ozonation. Our result opens new avenue for converting other natural gas liquid components to liquid oxygenates and upcycling of waste plastics. Finally, I want to acknowledge the funding supports from the National Science Foundation and Kansas Board of Regents. Also, we thank the CEBC industry partners for their feedback. I would also thank you for your interest in our work.